Dear students, today let us study about the photolysis of acetaldehyde. It is a photochemical reaction. Acetaldehyde undergoes dissociation in the presence of the light radiation from 250 nanometer to 310 nanometer. The reaction may be written in this way, that is acetaldehyde CH3CHO, and it takes one quantum of radiation and it forms CH3, a free radical, and another, that is CHO, another free radical. This reaction takes place in between 250 to 310 nanometer. 250 to 310 nanometer. Now, this is a photochemical reaction. It is a primary process. Here, one quantum of radiation is absorbed by acetaldehyde, and that is methyl free radical is formed, and acetate, that is acetyl free radical, is also formed here. These are the free radicals. Then it may take place, we may place it as the K1. Rate constant of this reaction may be taken as equal to K1. Now this is a chain reaction. It involves the number of steps. In the second step, that is acetaldehyde reacts with one, that is free radical, and it forms one molecule of methane, and CH3CO is formed. It is an intermediate compound is formed. This is, and it takes place with rate constant K1. This rate constant may be represented as K1. In the second, that is next step, sorry, it is not K1, it is taken as equal to K2, rate constant. First one is K1, second reaction K2. Then this, the intermediate CH3CO dissociates to give CH3 free radical and carbon monoxide as one of the product. Then it takes place with the rate constant, suppose this is K3. Then the last step involves, that is CH3 dot, that is free radical, reacts with another molecule of CH3 dot with rate constant K3, and it forms C2H6, that is methane. Okay, these are the reactions which are taking place in this photochemical decomposition of acetaldehyde. Now we may name this reaction as a number, equation 1, and this is equation 2, equation 3, and this is equation 4. These are the names. Now here, these are the number of products are there. Out of them, for the kinetics, we are going to study about this carbon monoxide is considered as the important product. Okay, it is the main important product or the final product like this. Thus, the rate of reaction depends upon the formation of carbon monoxide formed. Rate of reaction is nothing but the rate of formation of carbon monoxide. Thus, we may write that is rate of reaction is nothing but dCO divided by dt. dCO divided by dt, which is equal to, what is that? Rate constant K3 and concentration of CH3CO. This is an intermediate compound. Okay, we may call this reaction as equation number 5. Equation number 5. Then in the second stage, that is another compound formation. There is a formation of, this is CH3O and CH3. These are the different products. We are going to use them. Now here, one of the intermediate compound is CH3CO. That is D formation of CH3CO divided by dt. CH3 divided by dt. Here, according to this reaction, this, that is CH3CO, the intermediate is formed. That is equal to K2 into concentration of CH3CHO into concentration of CH3 dot, that is methyl free radical. Okay, this is formation of this intermediate compound. And the second one is decomposition, that is decrease. Here this is formed, here it is consumed. That is minus K3 K3 into concentration of CH3CO. We may take this equation as equal to 6. Now another important product, that is formation of methyl free radical, that is CH3 dot divided by, that is dt, is equal to, how this CH3 is formed? One is from this reaction. We may write it as K1 into concentration of this. But this is a photochemical reaction, that is a primary process, photochemical reaction. Here the rate of reaction depends upon intensity of light radiation absorbed. Intensity of light radiation absorbed. Suppose this is IA is the intensity of light radiation absorbed. Therefore, rate of formation of methyl radical depends upon the intensity of light radiation absorbed. Thus, this reaction it does not depend upon this, but it depends upon this. It is a photochemical reaction. One. Okay. According to this reaction, this methyl free radical is formed. One. Then another one is, here it is consumed, or let us take first formation. According to this also it is formed. That is plus K3 into concentration of this intermediate, that is CH3CO intermediate. Okay, this is formation about this. Then what about the consumption or the absorption? Absorption is done according to this. This is minus K2 into concentration of this acetaldehyde, that is CH3CHO, and concentration of CH3 dot. Okay, according to this reaction it is absorbed. And another one is, the absorption is this. This is minus K4. What is that? K1, 2, 3, 4. This is K4 into concentration of this methyl radical. That too square, because it is 2 times it is used. Okay. Now this reaction is taken as equal to 7. Totally, these are the 2 reactions taking place. But here, one thing you have to remember, how much amount of methyl, that is this intermediate is formed by these 2 processes. By this processes it is formed, and by this process it is absorbed. Thus we may apply this is equal to 0. That is steady state principle may be applied here. Change in, that is the formation of this is totally it is 0. Similarly, the formation of methyl acetate is also taken as equal to 0. That is, here it is formed by this reaction, and it is formed by this reaction, and it is absorbed by this reaction, and it is absorbed by this reaction also. Totally, this is also taken as equal to 0. It means if we apply the steady state principle to the overall system, whatever the amount of this intermediate is formed, it is consumed by this reaction. The total at a particular stage, the concentration remains constant. Similarly, at a particular stage, concentration of methyl acetate, that is methyl free radical, formed here and here also formed. Here it is absorbed. Here it is absorbed. Totally, at a stage, the rate of formation of methyl free radical is equal to the rate of absorption of methyl free radical. Thus, we can apply the steady state principle. Means steady state principle is made equal to 0. Rate of formation equal to rate of absorption. Here also rate of formation is equal to rate of absorption. Then it is made equal to 0. Okay, we got these things. Then we want to apply this, make equal. This is also equal to 0. This is also equal to 0. If we subtract one from the another, abstracting one from the another, 0 minus 0, again we are going to get the 0. Thus we can use equation, what is that? 7 minus equation 6. What happens? Equation 7 minus equation 6. 7, this IA as it is. Okay, one factor, that is IA, that is intensity of light radiation absorbed. We are taking this minus this. Okay, this minus this. Then here K3CH3O is there and this K3CH3O is there. These gets cancelled. Okay, and K2CH3CH3 and K2CH3CH3 this also gets cancelled. Then you are going to get only this. This is Ia minus K4 concentration of CS3 dot square is equal to 0, because this equation is equal to 0 as well as this equation is also 0, means 0 minus 0, again you are going to get the 0. Okay, this is equal to 0. Thus you may write that is CH3, that is methyl free radical square is equal to, what is that, Ia divided by K4, Ia divided by K4. And if we remove this, this becomes square root of this. Okay, if we remove this, this is equal to square root of this. Thus, by subtracting one into the another, you got another equation. Suppose this is equation 8 and this is equal to equation 9. Now, according to this equation, K2CH3, let us write it once again. K2 concentration of CS3 CHO and concentration of CH3 dot is equal to K3 CH3 CO, because this is equal to 0 means we can take it this side. This is equal to this. If we take this side, that is K3 into CO. K3 into CO. Now, according to this, according to the equation 5, dCO divided by dt. dCO divided by dt means rate of formation of carbon monoxide is equal to K3 into CH3CO. K3 into CH3CO concentration. And K3 into CH3CO equal to this. Thus we can write this is equal to K2 concentration of CH3CHO into concentration of CH3 dot. Okay, thus you can substitute the value of CH3 dot in this equation. That is equal to K2 into concentration of CH3CHO, acetaldehyde, and this is equal to square root of Ia divided by square root of K4. Okay, thus we can rearrange this. That is K2 divided by root K4 1, and this is root I, that is intensity of light radiation absorbed, and concentration of CH3CHO, concentration of CH3CHO. Okay, thus this is one constant, that is second reaction rate constant. K4, the fourth reaction rate constant, and square root of constant is a constant. Totally this may be substituted by another constant K, then root I, then concentration of CH3CHO. Okay, this is equation 9 and we must take it as equation 10. Equation 10 states that rate of this reaction, that is rate of formation of carbon monoxide, is equal to K into root I into CH3CHO, that is acetaldehyde. Okay, thus the rate of reaction depends upon acetaldehyde concentration as well as square root of intensity of light radiation absorbed, and this is one constant. Thus the rate of reaction is, we got this final equation, that is dCO divided by dt. This is the final equation for the rate of the reaction. Now next thing is about the quantum yield. Quantum yield is represented by pi. It is nothing but the rate of formation of reaction. Rate of reaction is nothing but the rate of formation of carbon monoxide. Rate of total overall rate of reaction is nothing but the rate of formation of carbon dioxide. or the quantity of reactants reacted. Rate of carbon monoxide formation. Okay, we have considered only this divided by the rate of intensity of light radiation absorbed, that is nothing but the IA. Thus we may write this rate is equal to this, that is K root I into concentration of CH3CHO aldehyde acetaldehyde divided by IA. Okay, and we may write this is equal to what is that? IA, that is K remains as it is, or let us write here, that is K remains as it is. Then IA square root IA means square root IA in the denominator, that is intensity of light radiation absorbed. Then concentration of CH3CHO, Thus the rate of this reaction depends upon this rate constant and the intensity of light radiation and the concentration of acetaldehyde present. Here the rate of reaction depends upon that is directly proportional to concentration of acetaldehyde and directly proportional to the square root of intensity of light radiation and this rate constant. Then quantum yield is equal to, that is nothing but the rate of reaction divided by rate of light radiation absorbed, or the amount of substance reacted in a given time and amount of light radiation absorbed in a given time. Thus this is the rate of this reaction we may take. Then divided by IA intensity of this can be made equal to K into CH3CHO divided by IA. This is the expression for the quantum yield. Now about the importance of this. What we are considering here, there are the number of reactants and number of products. But out of them, one important product, that is carbon monoxide, is used to calculate the rate of the reaction. Here methyl pre-radical is formed, and in some other reaction it is azoconjugate. And acetaldehyde is used here as well as here. And that is methane is formed in this reaction, and that is ethane is formed in this reaction. But totally to determine or to calculate the rate of the reaction, the concentration of the carbon monoxide is used. Okay, rate of the reaction is nothing but the rate of concentration of carbon dioxide. This is one. Then next thing is, what about the second point is about the effect of temperature. Now out of all these reactions, this is one photochemical reaction and it is a thermal reaction. Here to form this one hydrogen it gives to methyl group and methane is formed. It requires more amount of energy. More energy of activation is needed. Therefore, it requires energy. Thus, with the increasing temperature, rate of this reaction increases. Thus, this total, that is photolysis of acetaldehyde, the rate of reaction increases with increase in temperature. Means the effect of temperature, one thing. Then next thing is about the effect of pressure. Here, suppose this is one reactant and these are the two products. All these are the gases. I have not shown here, but these are all the gases. This is a gaseous reaction. As initially itself I have told that this is a gaseous reaction. All the products are gaseous. If one molecule of a gas gives two molecules, means pressure increases. Thus, with the decrease of pressure, the forward reaction increases according to the Le-Chatelier's principle. Thus, with the increase of pressure, the reaction is suppressed. That is, quantum yield decreases as well as the rate of reaction decreases. Okay, one thing. Then what happens with the decrease of pressure? With the decrease of pressure, the rate of reaction increases. Okay, this is one way. But actually it depends upon the temperature. If the temperature is at 200, not temperature, but the intensity, that is the light radiation, the wavelength of the light radiation or the energy of the light radiation. If the energy of the light radiation is, that is 250 nanometer is used, with the increase of pressure, this intermediate free radical forms the glycol. That is glycol, CH2, the C double bond, OH, C double bond, OH, that is one glycol is formed. Means then glycol is formed, the molecule there is decreases, again the rate of reaction increases with the increase of pressure. Therefore, this takes place at the lower wavelength, means higher energy. Whereas at the higher energy, with the decrease of pressure, rate of reaction becomes fast. Means here the pressure does not work independently. It depends upon the wavelength of the light radiation used. If the wavelength, that is 310, or this range above 300 is used, with the decrease of pressure, rate of reaction becomes more. Whereas with the 250 is used, or less than the 310 is used, here with the increase of pressure, rate of reaction should decrease. It should take place in the backward direction, but instead of that, again it increases. It depends upon the some other product is formed, that is glycol is formed. These are the effect of temperature, effect of pressure, and that is the effect of light radiation on this reaction. With this photolysis of acetaldehyde over, that is, it takes place at a 250 to 300 nanometer. On this range, in this whole range, this reaction takes place, but it shows the effect of pressure depending upon the wavelength. Thank you, one and all.